A very warm good morning to all the delegates and participants. You all are welcome to the 21st International Workshop on Physics of Semiconductor Devices. We will start the proceedings of the conference with Saraswati Vandana.
देवै सदा वन्दिता सा मां पातु सरस्वती भगवती निशेष जाड्या
I invite Professor V. Ramgopal Rao, Director, IIT Delhi, to give the opening remarks.
Thank you very much, Professor Dr. Saraswat, Dr. Seema Vinayak, Professor Vikram Kumar, Professor Ganguly, Professor Rajendra Singh, and all my colleagues here. Thank you very much for joining this event. Good morning, and I think this Iwpsd, as you know, this is the 21st edition of this conference. Started way back in 1991. In fact, we have all grown up attending this conference. We attended it as students. Now I think we have all been considered old enough. I think it has been maintaining the tradition. This is one conference where all the top-notch scientists from all over the world come and present talks, and many in India have had an opportunity to listen to them and learn from them. And this has also resulted in many collaborations between Indian scientists and scientists abroad. That is one additional purpose this conference has served, like all other good conferences. And particularly for semiconductor materials and devices, this has been the most well-known conference from India. And last one, as I remember, was in SN Bose National Center for Basic Sciences in 2019, and usually attended by 600 to 700 people. When it was in the physical mode, and because of COVID, of course, it has moved to the online format. But I also see that all the organizing institutes, IIT Delhi and SSPL, in association with the SSD, SSI, I think they have utilized this opportunity to get many top scientists to deliver talks during the conference. Because it's virtual mode, it was easy to have many top-notch scientists to present it from their respective places. And the conferences covers wide areas of semiconductor devices, starting from compound semiconductors, semiconductor crystal growth, memory, logic devices, photovoltaics, and MEMS and NEMS devices. I think it has come out very well. It's one of the finest technical programs for any conference of this nature. I'm sure we will all have a lot of learning from this conference in the next 4 days. Yesterday were the tutorials, as I understand. So I think all the best wishes, and happy learning for the next 4 days. Thank you very much.
Thank you, sir. I now invite Professor Vikram Kumar, Chairman, Society for Semiconductor Devices, and Honorary Professor, IIT Delhi, to give brief remarks about Iwpsd.
Dr. Saraswat, Professor Ram Gopal Rao, Professor Ganguly, Professor Rajen Singh, Samresh Das, all the participants, and ladies and gentlemen. It's my pleasure to welcome you to this 21st edition of the International Workshop on Physics of Semiconductor Devices. As you know, semiconductors are the base for the modern society, influencing all aspects of modern life. Ever since the invention of transistor in 1947, they have determined the technological growth in all fields, be it communications, computation, entertainment, defense, aviation, medical transportation, or any other field. The progress is ultimately limited by the availability and the advances in semiconductor technology. With time, more and more exotic materials are joining the semiconductor family to meet the increasing demands of modern society. The classical definition of semiconductor given in the undergraduate solid-state physics books has now so many exceptions. Materials like amorphous semiconductors, organic semiconductors, polymers, 2D materials, ultra-wide bandgap materials are now all part of mainstream semiconductors and playing an important role in active devices. This series of international workshops on the physics of semiconductor devices has covered this transformation over the last 40 years. This conference was initiated 40 years ago in 1981, not 1981. By Professor Suresh Jain by inviting a galaxy of top semiconductor scientists of that time. Ever since then, workshop has been held alternate years and provided a window for Indian researchers to the latest developments in semiconductor materials and technologies and devices. Initially, the events were organized by individual efforts, primarily driven by Professor Jain. But in 1997, the Society for Semiconductor Devices was formed to formalize this process and provide continuity. So, on behalf of Society for Semiconductor Devices, I welcome you all to the 21st edition of the Iwpsd. Due to unfortunate circumstances currently prevailing throughout the globe, we are holding the workshop in online mode this year. We'll miss out the excitement a young researcher feels while discussing the problem with a leading expert whose papers he'll be reading, the kind I felt when I presented my poster in 1981. But I hope invited speakers will give some time for the chat box and try to make up for the missing personal contact. Professor Rajen Singh and the technical committee and the people at SSPL and IIT have done an outstanding job of putting together a very busy schedule of high quality talks over the next 4 days. They've done a lot of hard work with the hope that participants will take full advantage by listening to all the talks. I hope you will not disappoint them. I wish you all a fruitful participation in the Iwpsd 21 and success in your semiconductor journey. Please stay safe and stay healthy. Thank you.
Thank you, sir. I'd like to invite Professor Rajendra Singh, Chairman, to provide information about Iwpsd 2021.
Good morning. So, respected Dr. V.K. Saraswat, Honorable Member Niti Ayog, Professor V. Ram Gopal Rao, Director IIT Delhi, Professor Vikram Kumar, Chairman Society for Semiconductor Devices, Dr. Seema Vinayak, Director SSPL Delhi, Professor A.K. Ganguly, Deputy Director IIT Delhi. Today's keynote speaker, Professor Lars Samuelsson from Lund University, Sweden, and SUS Tech, China. all plenary and invited speakers, contributors, and attendees. On behalf of the organizing committee, I cordially welcome you all for this 21st edition of International Workshop on the Physics of Semiconductor Devices. It gives me great pleasure to speak to you this morning at the inaugural session of Iwpsd 2021. This year, the Iwpsd is being organized in virtual mode only due to the prevailing COVID situation worldwide. A global situation has unfolded in the past 1 year or so, and that is the unprecedented semiconductor chip shortage in the world, which is affecting industries like electronics, IT, automobiles, and so on. So it is under this backdrop that the current edition of Iwpsd is happening, and it has highlighted the importance and significance of semiconductors and devices in our everyday life. Now I wish to provide you some information about Iwpsd 2021, which is being organized by IT Delhi in collaboration with SSPL Delhi and in association with Semiconductor Society of India, SSI, and Society for Semiconductor Devices. The workshop will be held from 14 to 17 December in online mode. During Iwpsd, we will have 11 symposia with topics such as 3 nitrides, 2D materials, flexible electronics, photovoltaics, and emerging logic devices, device modeling, crystal growth and epitaxy, and semiconductor devices for quantum technologies. We also have yesterday a tutorial on 13th of December on the topics of 2D materials, devices for quantum technologies, and devices. There are 2 dedicated industrial sessions also on December 14, means today, and tomorrow, December 15. Moreover, Society for Information Display is also holding a 1 day dedicated session on flexible electronics and organic semiconductors. So regarding the speakers, there is one keynote talk today that will be delivered by Professor Lars Samuelsson. 8 plenary talks, including 1 from Applied Materials, and around 130 invited talks from experts in the area of semiconductors. Out of these 130 talks, around 70 are from outside of India, and including there are 21 countries represented, including USA, Germany, UK, France, Canada, Australia, Taiwan, China, and so on. There are about 340 abstract submissions by PhD students and young researchers. There will also be Best Poster Awards for this that will be announced during the closing ceremony of Iwpsd on December 17. With this kind of breadth and flavor of technical program in Iwpsd, I'm sure that the participants will definitely enrich and enjoy the workshop by attending the sessions and with academic discussions. I thank all of you for showing your keen interest and willingness to join Iwpsd 2021, and again welcome you most cordially at the inaugural session of Iwpsd. Thank you very much.
Thank you, sir, for sharing the information. I request Professor A.K. Ganguly, Deputy Director, IIT Delhi, to release Iwpsd 2021 Book of Abstracts.
On behalf of IIT Delhi and the organizing committee, I'm very happy to release the abstract book for the Iwpsd 2021.
Thank you, sir. Now I'd invite Dr. Seema Vinayak, Director, SSPL Delhi, to kindly introduce our respected chief guest and invite him for the inaugural address.
A very good morning. Although I'm very, very sure that there would not be a single face among the participants of the 21st IWPSD today who has not heard or who has not known Dr. Saraswat. Yet, I take this privilege to introduce him to the audience. It's a pleasant duty that I've been given to perform. So,
Imaji,
but
if you can be very, very brief, I will be obliged.
yes, sir. I know. I know that. I know that you do not want a very long introduction, so I will try to be extremely brief. Padma Bhushan Dr. V.K. Saraswat is a distinguished scientist of outstanding repute for his notable contributions to the scientific community. An alumnus of Indian Institute of Science for his master's in engineering and of Osmania University for his doctorate, Dr. Saraswat formerly led the Defense Research and Development in India as Director General DRDO and scientific advisor to the Minister of Defense. He is credited with the development of indigenous Prithvi and Agni missiles and the two-tiered ballistic missile defense system. As the head of DRDO, Dr. Saraswat played a pivotal role in providing impetus to many programs that include command, control, communication, storage, transportation, and deployment infrastructure for strategic nuclear assets, flight evaluation of long-range subsonic cruise missiles, long-range radar command and control centers for defense against adversaries, and cybersecurity R&D. Dr. Saraswat's contributions do not just end with the Department of Defense. He has served as the chair in several advisory councils that include those of Indian Oil Corporation and National Thermal Power Corporation. As the Homi Bhabha Chair Professor and Consultant to IOCL R&D, Dr. Saraswat evolved a roadmap for the development of alternate energy systems. As chairman of NTPC R&D Advisory Council, he prepared a similar alternative energy technology development plan focusing on clean coal technologies and advanced ultra supercritical thermal power plant to work on efficiencies that are much better and on highly reduced greenhouse emissions. As chairman of the Committee for Development of Indian Microprocessors, he led a team to evolve the configuration of the microprocessor for Internet of Things, smart cities, and other ICT applications. He also laid out the strategy for development with DAITY, CDAC, IIT Madras, IIT Bombay, and SCL Chandigarh. Two devices have already been developed by IIT Bombay and IIT Madras in this field. He has evolved a concept document for setting up the Indian Railway Research Institute, Shrestha, for Indian Railways, which would propel indigenous designs and manufacturing in programs such as high-speed rail system and dedicated freight corridor and usher in a new era of R&D in the railways. As member Niti Aayog, Dr. Saraswat has initiated the methanol economy program for transportation energy generation. To this end, production agencies, academic institutions, and petro refineries have been brought together to further the cause and as part of this initiative, M15 gasoline blend, methanol cooking stove, methanol fueled propulsion for inland waterways, and methanol fueled gensets are being introduced in the country. At the academia and industry level, R&D in the gasification of high ash content Indian coal has been undertaken. Dr. Saraswat also chaired a committee on technical textiles and prepared a roadmap for the futuristic growth of this sector in India. He has also chaired a committee for framing a roadmap for Make in India in body armor. The excerpts from the committee's reports were later used to frame BIS standards on body armor. Dr. Saraswat led an empowered technical advisory committee for the development of national supercomputing systems. Configuration and strategy for development have been evolved, and the program has been launched as a multi organization mission. He is the recipient of many awards that include the Padma Shri in 1998 and Padma Bhushan in 2013. With this, I now request Dr. Saraswat to deliver his inaugural address.
Thank you, Simaji. Thank you very much. I hope I'm audible.
Yes, yes, very much, sir.
I'm very happy to be part of this today's inaugural session on India's international workshop on physics of semiconductor devices. I thought of talking to you about India's semiconductor manufacturing strategy rather than going into the physics, because physics of semiconductors is beyond me. It is not a subject which I can spend much time on that. But certainly whatever I understand is all because of the interaction with all the experts like who are present here. I'll give you a glimpse of what is happening globally as far as the semiconductor industry is concerned. All of you know that in 2019, before the pandemic, the global sales used to be of the order of $412 billion. The world semiconductor trade statistics, which give the market, and they predicted that by about 2020, 2021, this number will reach to about 426 billion. And if you look at what are the countries which are actually responsible for making the major contributions to this, I find that in the global market, US has got a share of about 47%. And the key emerging semiconductor applications continue to grow in terms of the end use demand. All of you are practitioners of some of them, like artificial intelligence, quantum computing, advanced wireless networks, and smart cities, semiconductor, and smartphones, and a variety of things which are actually emerging today. In terms of materials, if you look at it, what Dr. Vikram Kumar mentioned, and I think the whole conference is going to be focused on the materials and the devices. I personally believe that silicon, in terms of the major producer of silicon wafers, China is the largest producer of silicon, followed by the United States. That is the present status. Recently, we had a conference in India from the Niti Aayog, and I was trying to see how we can indigenously produce silicon in our country. And I find some of the institutions like CMET in Pune and CPET in Hyderabad, and a few one professor in one of the private engineering colleges, they have been able to make silicon wafers to a certain extent on the lab scale. But I think we have not been able to take it to a level where we can convert it into a commercial electricity. When you look at germanium, which is a chemical element which is similar in appearance to silicon, this is also mostly produced in USA, Canada, Russia, and Belgium. We don't have that in our country. The major material which is being used for a variety of the high frequency systems like gallium arsenide, which is being today used by SSPL and the foundry, which is the gallium arsenide GATEC foundry in India. It is again, it is more costly than silicon, and major countries producing gallium arsenide include China, Germany, Japan, and Ukraine. Other materials which go into semiconductors area which are emerging technologies, particularly for the high power systems like silicon carbide, gallium nitride, indium antimonide, indium arsenide, indium phosphide, selenium sulfide. They are all materials which are needed for photovoltaic cells and other similar applications. And the way the technology is emerging today, both for the SOC systems as well as the new materials, the new insulators which are emerging. For example, when you go for the next generation of devices, the 2D materials, neuromorphic systems will demand other systems which are required. So the material segment, as far as this particular technology is concerned, is emerging and emerging and emerging. What is bothering me today is, as a person sitting in Niti Aayog and also working with all of you, as to how we can have an ecosystem in the country for semiconductor devices. I find the material area in terms of the commercial production and also understanding and creating the kind of an ecosystem for development is desired there. Our all, even in the R&D institutions, all the wafers are imported and things like that. So that could also become a problem tomorrow, because all of us know that the materials are the key as far as the systems are concerned today. Now, what is the foundry business today? If you look at the semiconductor revenue for 2020, 2021, as I mentioned to you, is 460 billion. And percentage of foundry revenue as part of the total semiconductor revenue is about 19%. And all of us know that there's a growth of this market at the rate of about 6.75% over the forecast year between 2020 and 2025. So this is a very emerging market. And the India, as far as India is concerned, our import accounts in this area to about 8,818 million. This is a figure of 1819, and 65% of this comes from China. However, you know that what is happening today, there are trade tensions between the US and China, and they are causing some technology firms to rebalance their supply chains out of China and into India. I personally believe it's a kind of an opportunity for us, but the ecosystem which will promote this kind of a migration has to be strengthened. That is what we are working on that today. Now, why is it that we are looking today in India on major things? Because we are getting into electronics area, which will provide sensors and for internet and things, high-speed communication, big data and computing, green energy, security and encryption. And it will critically shape India's needs in terms of security, healthcare, agriculture, pedagogy, environment and energy. So electronics is a lifeline of the present and the future for any society. And that brings one major fact that you have so much dependence on that. We cannot live without semiconductors in this segment. Now, what does India do? We are importing about $400 billion of electronics about per year. And strategic import is 40 billion out of that, typically at the board or system level and high value in chips. The chips import is limited, but it is done by strategic departments, whereas the commercial segment, mostly it is the completely system level board import. That is what is happening. So there was a national policy on electronics, basically to focus on strategic needs of defense and aerospace, and to create a critical infrastructure for development of smart cities, e-commerce, banking, secure voting, 20 gigawatts of solar power, power electronics, radio frequency, and optical communication. This has been identified as part of the 2019 policy. But all of us know that the policy is, while it is going to be very, very important, but the dependence of our country on the import, both for the semiconductor chips as well as fully assembled unit, is very, very dangerous. I would like to quote here that Saint Ben Sasse, the Senate Select Committee on Intelligence USA, said, modern wars are fought with semiconductors. And there's an analyst called Maruf Raza, strategic affairs analyst of Times of India. We said the Chinese agenda is to have access to abundance of water to manufacture microchips. So you can imagine the kind of controls which can come in the way. And the recent developments which have taken place after the pandemic, the kind of disruption, I think with Mr. Rajendra Singh, which he was talking, of the supply of the semiconductor devices for the automobile sector, for the electronic sector, which has led to the reduction in the production of large number of automobiles in the country today. And we are really getting into what is called supply chain disruption in a big way. So how India can do, how can India come out of this? What is our capability in this particular segment? We have a semiconductor lab in Chandigarh, which is developing the VLSI devices and development of systems for telecommunication and space sectors. It works under the Department of Space today. It has got a capability to manufacture 180 nanometer kind of devices of both all kinds of microprocessors, analog, digital, everything. And they also have a center for MEMS manufacturing, which is also available. It actually got upgraded from about 350 nanometer to 180 nanometer. And there is a possibility that it will get further upgraded to about 65 to 45 nanometer. India has a very fast growing electronic system design manufacturing industry. Also, it has a strong design base for almost about 120 units. But what are the problems of this manufacturing? Because this manufacturing demands supply chain issues, which are very, very critical. On-time delivery is pivotal. In a consumer device market where speed to launch is critical, where device differentiation is based on feature functionality and by semiconductor capabilities, the relatively late involvement of the OEM's development process is no longer acceptable. Highly dynamic and vibrant technology requirements are there. Integration of analog, mixed signal and digital components in advanced nodes, resulting in more features, better performance, reduced costs, lower power use and faster time to market are required. And larger capacity requirements are required. Because if you want to be competitive, you can't be producing at 150 size, wafer size, and producing only about 700, 800 wafers in a year, in a month. That kind of a number is not acceptable. The logistics and distribution, given high volumes and increased frequency of orders, fulfillment timelines must become shorter. And to all this, India needs a huge requirement of the skilled workforce. Workforce is very, very important in this case. They have to, the chip manufacturers, whosoever is going to be private or public, will need to continuously develop new capabilities, whether this involves short-term adoption of functional integration to create multi-layer, multifunctional technologies, or a long-term capacity plan to adopt, as going from today's typical 300 millimeter wafer size to almost now everybody is trying to jump to about 400 millimeter wafer size. So what is the India's semiconductor roadmap? The roadmap for India is for building and developing a robust, sustainable and long-term semiconductor ecosystem. We need to have three important constituents: semiconductor manufacturing facility of the state of the art, and ATMPs, fabricate commercial fab, fabless ecosystem, and to top it all, when I'm talking to large number of academicians, it is important that there should be a very strong R&D for long-term sustenance of this kind of a system. Because if you look at the boutique which is available today, we need analog and mixed signal, we need digital, we need memory, flash, DRAM, we need for MEMS, silicon, we need photonics, and we need sensors. So we have the three areas which are very important in the power electronics: silicon carbide, the gallium nitride, and many of the discrete systems which are required to be done. So what India should do? India, if you compare yourself with China, China has about 170 fabs. So India should dream of at least 3 mega fabs and 6 boutique fabs. And R&D center is very critical for supporting this kind of an activity. Now, we have, as I mentioned to you, India's effort in this case have been limited, but we have the technical facility. In addition to that, there is a SITAR facility, which was part of the DRDO, which could build the silicon chips for defense and space needs. The Indian Institute of Technology, Bombay, has a Center for Excellence in Nanoscience, which has a lab-like facility in collaboration with Indian Institute of Science, Bangalore. Indian Institute of Center for Nanoscience and Engineering, which was established in 2010 to pursue the interdisciplinary research on the nanoscale. We have our own SSPL, SEMA-G is here, which is doing wonderful work as far as the semiconductor materials and devices are concerned. But all of them presently remain within the domain of what we call as prototype. CDAC Pune has been entrusted with the mission of development of an indigenous design of a family of microprocessors, IP, SOCs, an ecosystem supporting the product development to meet India's requirement for strategic, industrial, and commercial sectors. And what is needed, as I mentioned to you, in addition to setting up the commercial fabs of the latest variety, what is needed is a long-term focus on the R&D. For long-term self-reliance in the semiconductor, the government should consider setting up a dedicated research institute on similar lines like IMEC, Belgium. This institute will be a research-only institute with focus on semiconductor process, new materials, sensors, and newest technologies. We have to set up a National Institute of Semiconductor and Electronics Research only institute with focus on applied and fundamental, and we need funding for that. Almost allocate about $1 billion to $2 billion for 5 years so that we can jump to the next generation of things like quantum computing and things like that. So long-term sustenance of the R&D is very, very important, where we can do a large number of these activities. And this will also help to develop the human resource for R&D fab, which need to be laid out, keeping in view the existing research and various IITs and other institutes. Silicon should be the main focus in setting up the fab. Gallium arsenide, gallium nitride technology in either SCL or the main fab should also be coordinated through this effort. The MIT would need to take up ATMP and product development as important and challenging areas. So the plan should be that we should have a very good fabless ecosystem also to support this, and at least 100 fabless startup companies in the next 5 years should be set up. Create about $500 million of seed fund for these startups. Provide about 25% R&D subsidy to the fabless product companies. Provide PLI benefits to the domestic fabless companies. A special focus on chips in important and critical areas like the communication, 5G and 6G tomorrow, and Wi-Fi, state-of-the-art microprocessors for mobile and other devices, and tomorrow AI and ML specific chips. For example, now we are all talking of AI compatible chips today. Intelligent edge applications for IoT applications, metering and STB, chargers, inverters, and others. So there's an entire segment of fabless systems which need to be designed and ultimately manufactured in our system. Now, if you want to see what is the present status, we have today globally 14 nanometer FinFET technology with about 18-inch wafer. Cost of the fab setup is more than about $8 billion. So I have been advocating that India may not be able to set up a 14 nanometer fab, but our node should be today 28 nanometer, so that we can tomorrow work through our own R&D and go to 14 nanometers or 7 nanometers. That is what we are talking of. The 180 nanometer foundry can be further upscaled to about 90 meters or 45 meters at SCL, which will be responsible for taking care of the memory and analog device and mixed signal devices, and to a large extent the MEMS requirement is there. So fabrication of the integrated chip design, fabrication and testing facility, large number of ATMPs have to be also done. So state-of-the-art fab may be set up in the public-private partnership to support the design worldwide. Develop a skilled manpower for design, fabrication, packaging, and testing of ICs. Establishment of electronic packaging and automatic testing facilities to support the chip manufacturing ecosystem globally. It's not just for India. So what is needed is for Atmanirbhar strategy for self-reliance in electronics and semiconductors should be that there should be a national electronics mission which should directly report to the Prime Minister. It should have 3 segments: research and development, as I mentioned to you, with National Institute of Semiconductor and Electronics Research, where we can spend something like $3 billion. Products, in the products we should have electronic systems and fabless chips and ICs, which will be about 20% of the investment, which is about $6 billion. And for manufacturing, we should have electronics EMS and semiconductor fab and ATMPs, about 70% investment on that, which will be about $21 billion. So $30 billion is needed as investment over 15 years if India wants to really come out of this critical situation. And skilling of manpower development, infrastructure and enabling business environment, raw material production like the wafers I was talking of, equipment and supply chain that has to be done. And no wonder we cannot do it all by ourselves. So collaboration with long-term good policies with government to government, with agencies like Taiwan, Israel, South Korea, Japan, and US. It is important that we get into all of them. So to conclude, I would say semiconductor R&D center is needed for cost shared translation of R&D to manufacturing, for commercial and strategic products, consistent technology and product development initiation. Since corporate research is expensive, we must work towards research cost sharing. Government shall provide consistent cost sharing vis-a-vis startup to support them. Programs and funds for disruptive technology incubation should be also done. So this is what I personally believe, and I'm finding with what is happening today, along with the Ministry of IT and under the leadership of our present new minister, I think things are moving in the right direction. There is a possibility that we will have at least 2 commercial fabs, 1 R&D fab, and the upgradation of the SCL, which may take place in the near future. And PM Stack has already started looking at how to scale up the manufacturing of wafers in the country, of both the silicon wafers as well as gallium arsenide and gallium nitride wafers. These are, and silicon carbide. So these are the major areas where the push for materials will be taking place. But I think this workshop should also tell us how India can augment its research capability in the development of the next generation of materials which are going to be needed, how the Indian ecosystem can be strengthened for material development. If that can be addressed, like we are now addressing how to go for the foundry, but the basic thing for a foundry will be the material. So how that can be done, if the workshop can come out with that, whether we can do an integrated approach between SSPL, IISc, IIT, and many other institutions who are into the solid state materials, if they can all work together and make a mission mode program for development of next generation of materials for semiconductors, I think it will be a great job. I wish the conference all the best, and the workshop should be able to lead us into the right direction. Thank you very much and wish you all the best.
Thank you very much, sir. Thank you for spelling out undoubtedly the critical significance of semiconductor materials and devices for the electronics industry, and in inspiring us to put in unabated efforts to become Atmanirbhar in the field of semiconductor chips. We are extremely thankful to the guidelines you have provided for achieving this through sustained R&D, feeding to fabless manufacturing and to indigenous fabs. It is really very, very heartening to see the kind of attention semiconductor industry is now getting from the government, and it will not be long. We feel confident that it will not be very long before India has made a mark in this area. Thank you very much.
Thank you.
Thank you, ma'am. Now I'd invite Professor Samresh Das, Secretary, Iwpsd 2021, to give vote of thanks.
Good morning all. I feel honored and privileged to get the opportunity to propose a vote of thanks. On behalf of the organizing committee, I convey my deep regards and hearty thanks to our honorable chief guest, Dr. V.K. Saraswat, member of NITI Aayog, for his kind presence and very inspiring inaugural address. I am very thankful to Professor Ram Gopal Rao sir, Director IIT Delhi, for his continuous support and advice towards the successful organization of Iwpsd 2021. I am also thankful to Professor Vikram Kumar, former Director SSPL and NPL, and Dr. Seema Vinayak, Director SSPL, for their help and support at various stages. I would also like to thank the administration of IIT Delhi, SSPL, Society for Semiconductor Devices, Semiconductor Society India, and Society for Information Display for their continuous administrative support for organizing this conference. I am thankful to the Iwpsd 2021 Steering Committee members and International Advisory Committee members for guiding us to hold this conference. I take this opportunity to thank all the technical committee chairs and members who have arranged such a high quality program. My special thanks to all the keynote speakers, plenary speakers, tutorial speakers, and invited speakers and session chairs. I am very thankful to all the sponsors for this conference for their generous financial support. The sponsors for this conference are Society for Information Display, Applied Materials, Samco, Oxford Instruments, Silicon Power Corporation, Amitech Instrument, Entity Advanced Technology, Silicon Electronics, Excel Instrument, Dynatalk Instrument, Wraith India Private Limited, Lab India, Agmatel, Forvision Instrument, SK Nobel Materials, Hind High Vacuum, and McQueen Private Limited. Special thanks to Spinjar for arranging to bring out the proceeding. I'd also like to thank the local organizing team from SSPL and IIT Delhi. Special thanks to Dr. R.K. Sharma and Dr. Kapoor for organizing the tutorial session. I'd also should not forget to thank the volunteer and student teams who put their last complete 1 week in arranging this conference. In this regard, special thanks to Dr. Sheetal Dewan, Dr. Manikant Babu, and Dr. Nandan Kumar Singh and Mr. Sheep for their continuous support and hard work for the last 2 months. I would like to thank our digital partner, Dreamness Conference Management Private Limited. We expect a smooth conference over the next 4 days. I am also thankful to the participants who have joined in such a large number. I once again grateful to everyone whose contribution has made this conference a success. Thank you.
Thank you, sir. Now I invite Professor A.K. Ganguly to kindly introduce our keynote speaker and chair the session.
Professor Ram Gopal Rao, may I take leave? I have some more commitments. If you
Sure,
don't mind.
sure, Dr. Saraswat. It's okay. Thanks a lot.
Thank you.
Good morning, everybody. It is my extreme pleasure that the plenary lecture today is being given by Professor Lars Samuelsson, who is a highly distinguished professor of solid-state physics at the Lund University in Sweden. He is a distinguished professor at the Southern University of Science Technology, Shenzhen, China, and director of the Nanoscience and Applications at SUSTEC, Shenzhen, China. He did his PhD at Lund University and was at IBM in San Jose, and later as a professor at Chalmers University of Technology. He then became a professor of semiconductor electronics at Lund University. And most importantly, he created the first lab in Scandinavia called the Nanometer Consortium. And very early in nanotechnology, in 1988, etc., he had brought up this laboratory that's very early in the field of nanotechnology and semiconductor nanostructures. His main focus was on the growth of semiconductor nanostructures and looking at their properties. And more specifically, he worked on nanowires and was primarily the first person to show how you can effectively use nanowires and their electrical properties. He's the founder of several companies, including Q Nano AB, Sol Voltaics AB, and Glow AB. He's a fellow of Institute of Physics, American Physical Society, a member of the Royal Swedish Academy of Sciences, and the Royal Swedish Academy of Engineering Sciences. He was also appointed Einstein Professor of the Chinese Academy of Sciences. He is ranked 3rd on the prestigious journal Nano Letters and has a significant number of publications. I invite him, Professor Lars Samuelsson, to give his plenary lecture.
Thank you very much, Professor Rao. Can you hear me?
Yes, yes.
Okay, thank you. Dear distinguished honorable professors, organizers, dear Professor Rao, dear Professor Rajendra Singh, the chair, who was so kind to give me invitation to give this prestigious talk at the Iwpsd 2021. Also, I want to highlight my long-term relation with Professor Vikram Kumar. To me, you are Vikram, but of course, you're Professor Kumar. We had some good times together in the 80s when you were spending time in the physics department in Lund. We were working together. I also want to make a reference back to 2017, 4 years ago, when I had the opportunity jointly with my wife to be in Delhi for the Iwpsd 2017. So I'll turn on share screen, hoping that will work. Okay. Share. I have to do something. And here I do this. Do you see my screen now? Is my screen visible?
Yes, we can see the screen.
Okay. I thought maybe you lost me. Okay. So I'm going to talk to you over actually more and more spending time. Right now I'm in Shenzhen at the Southern University of Science and Technology. There are very interesting links between the two. I can maybe specifically for Vikram Kumar mention that yesterday on December 13, I was part of organizing a Lucia party, who you might remember from your time in Sweden, which is a special event when we're welcoming light with candles and specific songs and foods and drinks. You might remember that. Okay, so besides being in universities, let's see if I can up. Right now, I don't move my slides. Here, okay. So I'm also, as I heard, founder and chief scientist of a series of companies. I'll mention a couple of them as we go along, specifically those that have to do with gallium nitride things. First, a brief presentation of a little bit my academic research, very briefly, the way and Lund as a Center for Nanoscience, and also my engagement as academician. Then I say a little bit about these company things, because I think that has relevance in fields of advanced semiconductor research and technologies. Then I'll talk on what are nanomaterials, in general nanomaterials technologies specifically related to nanowires and related structures. I will then go to the core, the meat of the presentation, more technical. R&D related to what I call nano LEDs, meaning they are smaller than 1 micron in size, which is a way of realizing micro LEDs with high efficiency for all 3 colors. And that towards the end, I say a few words about my present job here as director of a new research institute. So I think you know Sweden. Let's see. You can see my pointer, maybe. Is it okay? Yeah.
Yes,
Well, this
we can.
I'm pointing at the red country, Sweden, which is a low population country, 10 million people, but it's a long country, more than 2,000 kilometers in length. So it's most of the population is in the south, and I'm located in Lund, live in Malmö, working in Lund in the very, very south. And from my home, I'm almost directly a bridge over to Copenhagen. So that's a hot space to be. The picture you see, Vikram remembers very well, I'm sure. That's the main university building at the university, and the symbol up to the right. University, 5 years ago, we celebrated our 350th anniversary as an academic university. Swedes are very much into nature. Swedes embrace nature, I say here. You can see in the winter time in April, you're going to see the Vasa Lopp race, which is a skiing event with 70,000 or so skiers racing over 90 kilometers, which is pretty serious skiing. That's winter. In the summertime, we very much enjoy being on the waters or close to the waters. But we're not only nature lovers, we're also very keen on high technology, just like India. And you can see some of these that I think you're pretty much aware of. I'm pointing at, for instance, Ericsson, communication systems. IKEA, I'm sure, is well known also in India, the Volvos, the Scania for the trucks and the cars. Spotify for the younger generation, ABB being a power transmission company, Sandvik doing specialized steel, and Alfa Romeo. Here you have Saab with the fighter planes, which is quite amazing. I think that a small country with 10 million people can sustain and support also academically all the know-how that is required to make fighter planes. Tetra Pak is a food packaging company, which I know is also present in India. I get reminded of every morning here when I have my morning coffee that I get milk out of a Tetra Pak with origin from Lund and Lund University. So what I did in 1988 was to realize, when I came back after a very young age professorship at Chalmers, coming back to Lund, that was the time when I could really do something new. And I switched lane from previously being primarily a deep level physicist. I think that's the status when Vikram and I worked together. To start the Nanometer Structuring Consortium, which we later renamed into Nano Lund, which was easier for people to remember. So the idea here is that you can see that the tree symbolizing what we're doing to the left, getting much of the nourishment from advanced synthesis, fabrication, advanced characterization, and theory, and then publishing in areas like quantum physics and material science, but then also doing applications towards electronics, photonics, solar energy, biophysics, neuro, nano, safety things, and you know, so that's the crown here is sort of where we published. I think I can also claim that Lund is one of the leading European centers also in terms of ERC funding, you know, big funding also from national and international big programs. So when I started this in 1988, I think we were 8 people. I think we counted 1 or 2 master students to make it look more impressive. Since we were 8 from the beginning, now you can see that when I handed over So what do we do? What can we do? Well, we try to contribute to sustainable society, for instance, with solar cell technology, nanomaterials for solar cells, the information society in general, novel devices, quantum computing, display technology, sensors, networks. Precision medicine is not my own area directly, but we have strong interaction with people in medicine and biophysics. And of course, maybe here I have more direct personal involvement, trying to create an industrial nanomaterials-based industry effort. So how do we do this? How can we do this? I think the core competences has to do with atomic scale precision. This is now from a picture from our clean room, which is pretty advanced clean room, called Lund Nano Lab, that we got heavy funding for 2004 to 2007 when it was inaugurated. Also very much related to advanced crystal growth. This is an example from the nanowire research. I think I'll come back to that a bit later. Also these nano devices like nanowires, so you can see a little nanowire here, being measured electrically and thermally in all kinds of physical investigations. And also I think this image shows a perfect array like a needle mattress. I think that's more well known in India than in Sweden. With actually indium phosphide nanowires created by a combination of top-down lithography and bottom-up self-assembly. It also, I can remind that now my successor, Professor Anders Mikkelsen, who is a very smart and competent surface scientist, both in scanning probe techniques and in connections to the MAX4, the synchrotron center in Lund. So I mentioned the Synchrotron Center. So this is now the city of Lund, where there are a lot of research going on where we are. In the center of Lund, you might barely be able to see, but there is a dome. I can say the dome is actually from 1032. The inner original sections of the dome still standing there from 1032. That's pretty old. In the background, you can barely see there is a bridge over to Copenhagen from Malmö. So up in this northeast part of Lund is now what we call the science village with the facilities. The synchrotron facility MAX4 is, I think, today the brightest synchrotron in the world for material science. And I think 2024 is very optimistic. I hear now it's more like 2026 when the European neutron spallation source will be inaugurated, but it's also going to be a rather unique performing center in its kind. When I'm not doing research and development, I'm also heavily engaged in the two academies. So this is the primary science academy, the Academy for Science, where we, among other things, we meet every year on December 10. Last Friday was the celebration. It was very much reduced this year. It didn't look like this. But here is sitting the royal family, the selection of people from the academy, the award winners, and some previous Nobel laureates. That's sort of the setting. Every year, this year it was much scaled down. Unfortunately, I hope it's going to go back to normal next year. So we do all kinds of things there. I mean, with my background, I guess I knew quite a bit of what happened with this prize. 2014, when we awarded the physics prize to Akasaki Amano and Nakamura for the invention of the efficient blue light emitting diodes, enabling bright and energy-saving white light sources. So that's a very nice type of job to be involved. For instance, I was there, maybe one of the main hosts for these excellent three scientists. And for instance, I was hosting when Hiroshi Amano came down to Lund to lecture to the students, the Nobel lecture for the students in Lund, and also, social activities. Fun together. You see, it can be cold in Sweden in December, which Vikram Kumar knows very well. So that's Amano with an interesting little cap on his head. So a little bit of entrepreneurial activities. There are many companies coming out of the research environment. I circle in here. Two of them had to do with the nitrides because that's more relevant for my topic. Glow is an LED, a micro LED company, and Hexagon is gallium nitride in general, both for power electronics and for optoelectronics. We have then also, of course, all the collaboration with big industries in Sweden and internationally. So these, with the academic research happening, here you see the dome, by the way. The research happening in the university area, there's also a science park where there are many hundreds, I think 400 companies. And among them in this building complex here, we collected Glow, Q-Nano, Solvotex, and Hexagen, which is in the near connection to where the academic research is. In the foreground, you see actually the center where Ericsson and Sony Ericsson developed much of the mobile phone technology here in Lund. All that happened in Lund, actually. Yeah, clean room, everyone, all clean room more or less look the same. So we have a pretty advanced clean room, class 100, class 1000, depending on what we're doing there. E-beam lithography, focus ion beam, all. Glow, and then we did Solvotex, and then we did more recently Hexagen 5 years ago or so. And can you see, because I got a warning that the internet connection was weak. Is it still okay?
It's okay now. It's fine.
Okay, thank you. Okay. So with all this happening in southern Sweden, we actually developed very quickly the company Glow for LEDs initially, micro LEDs as times went on. So we actually outgrew all the facilities we had access to, and we moved to Sunnyvale, both for space, but also to get access to people with the industrial background, like the Lumiled research environment and several other LED-related companies. So Glow moved there and kept much of the more long-term materials research still in my group in Lund. So the thing that started actually as a university project before Glow was created was this idea to see if one can do something about the poor quality of gallium nitride the way you can buy it. Gallium nitride doesn't have a natural substrate, so either if that is grown on silicon or on sapphire or silicon carbide, you have very high dislocation densities, say 10 to the 8 to 10 to the 9 per centimeter square, which is of course a problem for some applications, not so bad as we know for the blue LEDs. There are built-in physical mechanisms that forgive these dislocations, but for other applications, it's very serious with the threading dislocations. So what we did in my group was to cover these commercially available gallium nitride on silicon or sapphire with a thin growth mask of silicon nitride in most cases, and then lithographically by E-beam or nano-imprint or deep UV, making small holes at the scale of 80 to 100 nanometers preferably. And then you grow out these perfect rods by, in this case, selective area growth. This is not catalytic grown, they are selective area. And you can maybe see that these are hexagonal faceted, so-called M facets surrounding these wires. You can see that this works also over large areas. Here, I think you can see that there's a very, very high density of dislocations in this green, the gallium nitride that you buy. Here you can barely see, this is the growth mask. This is this is the small opening in the growth mask, and this is where the nanowire that grows out. So this is now completely dislocation free. So the idea that we started with both in the university and when GLOW was created, it was to use this as a perfect single crystalline substrate to grow radially device structures. And that I think is seen here. So the idea is to first grow this N-type core material and then grow radially all the different heterostructures, the active layers, aluminum gallium nitride blocking layers, and the P-type outer surface. Here you can see, a little bit difficult to see, but maybe you can see the structure from this high resolution SEM image. You see you have a very, very critical optimization of the nucleation, which is enabling all these nanowires to be formed like this. So this was for a long time the main product being developed by GLOW. Actually, more recently, the nanowires are not in the focus of the attention, but it's still a very interesting technology. I think GLOW had the first high efficiency green LEDs based on the nanowires, which had 35 to 40% efficiency very early, actually. It's very challenging with the processing and the contacting of these structures. Of course, it has great advantages also in coupling out light, but you can do that in other techniques as well, specifically when you go down to very small LEDs. So this is a review article that we published jointly. Nate Gardner was the CTO, Chief Technical Officer, coming from Lumiled, but working for many years in GLOW. Unfortunately, about 5 years ago, he was given a probably a slightly better offer from a company called Apple. So he was not with the company for the last few years. So this might be interesting. It was published in Semi-Metals a few years ago. So GLOW is then today primarily doing planar growth and processing down to very small devices, planar devices. So for instance, here you see one of the industrial collaborations for a contact lens display with pixel sizes down to around 1.4 microns, really very small. I think that's more or less the best that I have seen being presented as an industrial project, but also for augmented reality, head-up displays, smartwatches, smartphones, and all these applications that it seems we can't have enough. So what was unique, I'll get back to that in a minute also, is that GLOW was, I think, the first company that demonstrated one and the same technology for blue, for green, and for red, enabling then one and the same technology also down to, it's been demonstrated for 20 microns all the way down, as we said, 1.5 micron sizes in this case. The second thing that was industrially, technically developed very deeply and seriously at GLOW in Sunnyvale was these laser-based, writing, release, transfer, and then sort of on-site welding onto the backplanes. The backplanes be either a CMOS backplane silicon or low-temperature polysilicon backplanes, which enables large area displays to be realized. So this picture you might have seen, it's been circling around a lot in the literature. So this is an example of a pixel 20 micron size here with one green and one blue, and two reds, since the red is much fainter than the blue and the green, which I can come back to, which is really one of the big challenges now. Here compared with, I think, maybe not a fully fair comparison, but this is what the main competition is doing the blue and the green in nitrides and the red with gallium arsenide and aluminum gallium phosphide, which has severe problems, both mixing technologies, mixing materials with different properties, and also assembling them into one and the same. But that's the approach that many companies still use. So what happened this summer, 20th of May, was a lot of articles around the world on the fact that the leading Silicon Valley nanotechnology company Nanosys actually acquired GLOW for a sum that I just know roughly. I don't know exactly how much, but it was probably very expensive because at that time GLOW had invested more than $200 million in these technologies that I just described. So from now on, GLOW is a part of Nanosys, and I am not anymore the chief scientist. I'm not on the leadership of the company. So now I can only be a spectator seeing what's going on. But I can still have good relations to them and also to the CTO of Nanosys, Homer Antoniadis, who is, of course, now leading both. Nanosys has traditionally one of the absolutely world-leading companies for quantum dots for displays and television screens. And of course, now they have both the leading quantum dot technology, one of the companies with the leading quantum dot technology, and the micro LEDs in one and the same company. It would be interesting to see what's going to happen with them. So this is a slide from Homer Antoniadis, the Nanosys picture. Here you see the pixel level, more and more advanced small sizes, and here you see the time. Yeah, this is the timeline, sort of. So with the old technology like plasma and edge-lit liquid crystal displays, today there's a lot of work, as you know, with mini LEDs backlit to LCDs. There's a lot of OLED producing white light, and then with the color filters, there's a lot of, the RGB OLEDs directly. Lots of the combination of quantum dots and OLEDs going on all over the place. I mean, as you know, in Shenzhen, where there are some of the largest primary companies, TCL and other companies in the area, developing these technologies also. So he also notes that the May 20 was Nanosys acquires GLOW AB. So in the near future, he says that micro LEDs are going to continue to grow strongly. The quantum dot combination with micro LEDs is going to be a big thing. And then he has the vision that 5 years from now, maybe it's going to be predominantly nano LEDs that is supplying very advanced technologies for displays. This is also the final slide that I got from him, for the different, goodness numbers like color, brightness, resolution, thinness, flexibility, contrast, viewing angle, and cost for these different technologies. And maybe not surprisingly, even seen the other slide, the only technology there where he says that he makes green check marks for all of them, but this can be discussed. I'm sure that there are advocates of OLEDs that say this is not right at all, but this is Homer Antoniadis and Nanosys picture. And with my title, you probably realize that I think nano LEDs will have a big role also in the near future. So for the sake of time, I'm not going to go into too much about the Hexagem. Hexagem is a company in Lund, still going on at the Ideon Science Park, where we develop low dislocation, high quality vertical device structures for power electronics, but also the photonics. So today, the present technology, which is not part of the GLOW technology, namely the platelets, that is my next topic, what we are primarily working on now. The IP and much of the industrial collaborations is with Hexagem also for the photonics. So the nanowires and nanomaterials, a little bit about that, a little bit of the historical background. Way back in the 90s, we were doing not the colloidal growth of quantum dots, but we did a lot of aerosol phase creation of quantum dots. I think this is a rather cute project we started that 1995. They're making an aerosol fume of in this case, gallium droplets, nano-sized, and then doing a size selection as using standard aerosol technology, differential mobility analyzer, size selections, and so on. And then putting that into a furnace where you let these gallium droplets react with, in this case, of the furnace temperature, how the diameter, let's take this one, the plus signal, the diameter was now unstable internet, this says. Okay, so this is now with the 10 nanometer particle diameter of the gallium droplets, and you see that as you go up in temperature, there is a kinetically induced transformation of these gallium droplets into gallium arsenide particles. So these diameters correspond to the same droplet being converted to gallium arsenide. That was quite fun. The other big effort we had in the from mid of 1990s was on transbicrystalline growth of nanowires. I think this is also stuff that has been going on also in India. And so here you see some examples of indium phosphide quantum dots formed by transbicrystalline growth when you try to grow a very thin film of a strain material like indium phosphide on gallium arsenide or indium arsenide on gallium arsenide. In this case, it's actually indium phosphide on gallium indium phosphide last matched to gallium arsenide. Well, it's not so important, but that's what it was. And here you see the facets that are formed measured by an AFM. Here you can also highlight Werner Seifert, who just recently turned 80. He left us almost 10 years ago, he left us, who was a fantastic crystal grower and who taught us a lot when he was a professor recruited from Germany, working in my group for a long time. So these quantum dots were used for very nanophotonics, like this paper, which I'm pretty proud of. Don Hessman was my student at the time. I think he had the first example of single quantum dot photoluminescence excitation spectroscopy, and time resolve spectroscopy on the single quantum object scale of these transbicrystalline quantum dots. We also did a lot of studies of excitons, charged excitons, bi-excitons, and all the kinetics between these different species, in this case published towards the end of the 90s in a science publication. Then there was a little bit of interference because at this time I spent a sabbatical half year in Tokyo, and I got very inspired by work going on at Hitachi in nanowires. So the quantum dots were a little bit reduced in effort once we had started with the nanowires. So what are nanowires? Nanowires are not carbon nanotubes and not nanotubes. They're really solid crystalline rods. Here's an example of what we grew with CBE, or Linus grew with CBE. There's the gold particle at the end in this case. Can be very long and slender. This, I think, is 55 nanometers and 10 microns long. This is now a gallium nitride nanowire, but it's much thicker because it contains these radial device structures that I mentioned for the development of GLOW's technology. So here's what was originally done in Bell Labs in the 60s. It was not nano, it was millimeter technology or 10th of a millimeter whisker technology, where they found that if you had a gold droplet, a gold particle positioned on a silicon substrate, and you infiltrate that with silicon from silane, for instance, then you're actually supersaturating this droplet. It would be a liquid eutectic metallic particle, and this excess material is actually transferred on growing on the interface to the rod and outgrows this structures. This is like a monolithic extension from the substrate. When it became nano, I think there were some other people working on this, but I primarily give the credit to Kenji Huruma, who was leading a very successful research effort at Hitachi Central Research Lab outside of Tokyo. And I said I was a guest professor at RICAN, and I spent many visits to him because I realized this is probably what I want to do in the future. And a few years later, in 98, 99, we got started, but so did other people. So at the very late in the 90s, Charles Lieber at Harvard, Pei-Dong Yang at UC Berkeley, Xiongling Wang also in Georgia Tech. But I think these three groups were sort of credited with maybe the greatest breakthroughs at that time, late 90s, early 2000. So in my group, I had a lot of good students working on, for instance, Ann Persson, did together with the people in materials chemistry, Rainer Wallenberg, who's the leader of the TM Center. We did a lot of in situ studies, trying to understand the structure of the crystals, the nanowire crystals, and how the different conditions for growth affects the actual crystalline structure. I had another very good student, Kimberly Dick, who came to me as a master student from Canada, from Waterloo. And she, when she came, I guess, got a crazy idea. I think, Kimberly, maybe we can make trees of nanowires. And she was willing to try that. And you see very quickly she got these trees growing. Yeah, initially, you can say the idea is, sorry, maybe let me quickly say the idea. First, you grow vertically, pointing at you these nanowires, and then you use those to attract by electrostatics smaller gold particles that land on the side facets of these hexagonal wires, similar to what I showed you before. And when you start growing again, these grow out only in specific directions. So you could also use that to form self-formed networks of millions or billions of interconnected wires. Not yet sufficiently good to make a perfect neural network systems, but I think it might in the future be worth giving a serious try. Yeah, this was the paper. Then, so she was just about to start a PhD work when she got the first Nature paper, which was a bit moralizing for the environment since he came as a very young student. But it was very good for her, and it was good for our research environment. You can say, are these useful? Well, like the networks, maybe. The first application of these structures is that we made the Christmas card that we sent to our friends all around the world. Maybe also Vikram got a picture of our Christmas tree Christmas card. Yeah, it was noticed all over the place. There's a new scientist about our Christmas trees, yeah. But I think maybe technically the most important breakthrough at this time, early 2000, 2002, actually, this was the nanoletters, this cover picture that you saw before, which is actually 3-5 heterostructures between indium arsenide and indium phosphide with ultra-sharp interfaces between them. So all the green here is indium arsenide, the red is indium phosphide. And these can be combined, although they almost differ 4% in the lattice constant, they can be combined with the efficient radial realization of the structure. So we say that I gave this a title that I maybe didn't think the editorial people would accept, but they did. Because the idea was the following: here comes an innocent, nothing suspecting electron in indium arsenide. It comes to this thing here, which is a thick wall, and it can do two things. Well, it either can stop on this side, or it can climb over, maybe with thermal excitation. You can, over here, you can use the fact that this is a very thin barrier, you can tunnel through, so you can make all kinds of tunneling-based devices, which we did. We had a series of many different modeling devices, one-dimensional devices. So here you see an example of one tunnel barrier here, indium phosphide, another tunnel barrier here, and in between this, the quantum dot, is like a quantum disk of indium arsenide. So this is the electrons tunneling through the devices. Yeah, we also did a lot of structural studies of these kind of wires. This is a self-formed repetitive rotational twin arrangement of the growth front, producing these very neat totem pole nanowires, published in Nature Nanotechnology. And this, I think, is a very neat crystal. Since this is all indium arsenide, it comprised of 8 monolayers of zinc blende cubic. Maybe you can see that. And then 8 monolayers of hexagonal wurtzite, again, the zinc blende. So this is a superlattice of wurtzite zinc blende, which has interesting band offset situations that gives very interesting optical properties and transport properties. And also the superlattice does interesting things to the phonon-mediated thermal transport. Yeah, as I said, we were the first to really combine nanowire growth with general technology, top-down patterning, and then bottom-up growth of arrays. This was my student who excelled in this, Thomas Mårtensson. Then this, of course, now we had the tools to interact with everyone, like people doing quantum physics investigations. This was an early paper. This is with Andreas Fuhrer, who was a postdoc for 3 years in my group, a fantastic scientist. He's now with IBM in Rüsselsheim. A second project, I have some slides showing a little bit more details on nanowire-based transistors. So I took the initiative, and I was leading a big European program together with all the European industries and research institutes, Max Planck, IMEC, and all these, on nanowire-based, called NODE, nanowire-based one-dimensional electronics, NODE, N-O-D-E. And Klaus Tillander was one of my leading partners in this. In this case, it was an indium arsenide vertical nanowire with a dielectric wraparound insulator and then a wrap gate. So it's like holding a water hose and controlling the flow of water, but in this case, the flow of electrons. Also a lot of collaboration with people in life science, like Jonas Tegenfeldt and Christel Prinz in this case, making actually core shell wires where you can etch out the cores and get fluidic channels connecting them to cells. You can do injection extraction of materials in single cell. This has been going on now without my involvement, but I had the original initiative for doing this, and I think it's still flying pretty high in the environment. Yeah, so this was this quantum physics investigation where we could directly measure the spin-orbit coupling by this avoided crossing in the experiment, which is of course a very important input to quantum information usage of these quantum dots. And this is now from the industrial project nanowire-based one-dimensional electronics, abbreviated NODE. This paper is from 2006. So then from then on, it's been very much also the industrialization, of course, the LEDs, I said. This is one of the original studies we did published in Science in 2013, creating the technology for nanowire-based solar cells. We've had a series of European programs, the last one on implementing these types of array solar cells on a silicon platform, together with, among others, IBM researchers in Switzerland. But that's not the topic of this talk. Also, a very novel means of making materials, nanomaterials. It was actually a second example of growing things in the aerosol phase, calling it still the aerotaxi with the flying wires, sending in size-selected gold particles into a furnace, letting them diffuse through a furnace at the controlled temperature for 1 or 2 seconds, and out comes a nanowire being 1 or 2 microns in size. This was published in Nature in December 2012, and later became the technology for Sol Voltaics, the solar energy company. So now we go to, looking at my clock, still going okay, about the R&D related to the nano LEDs, the main topic of my presentations, with the intentions to make all 3 colors with one and the same materials technology. So here I have to acknowledge also the people that have been contributing to what this dream of mine since I think 6 years ago I got the idea for this. So I call this ultra small indium gallium nitride nano LEDs based on relaxed C-plane indium gallium nitride template. It will become clear. If it's unclear now, it will be clear in a couple of minutes what this is all about. I want to acknowledge all the people involved in advanced growth and processing, specifically Shosha B, who is the leading MOCVD expert on this, who came to me as a young postdoc from Nanjing University's physics department in 2005 and has stayed around for more than 15 years now. He's really a key person in everything we're doing here. Anders Gustafsson, who is the cathodoluminescence expert, working very much together with Rainer Wallenberg in the TM. And down here we have some of the industrial friends, primarily Fari Badanish, who was the CEO of GLOW for 10 years in Sunnyvale, and now the connections also to Nanosys, and Mikael Björk, who is the CEO of Hexagon AB. He was, by the way, the first author on this red and green nanowire paper when he was still doing his PhD in Lund. That was from 2002. Later, he was for 7 years research scientist at IBM in Rüschlikon, Switzerland, and then coming back to Sweden when his children grew up and still go to a school. And he is now back in the stuff we're doing together as CEO of Hexagon AB, which is an interesting science story as well. Maybe this doesn't show up very clearly. We just published a writing book chapter on from nano LEDs to realization of RGB emitting micro LEDs with Shosha B and also with involvement of Fari Badanish and Shenzhen from GLOW. A book chapter in semimetals again in a volume dedicated to micro LEDs, volume 106, chapter 7, if anyone would be interested to look at the details. So this is, of course, not only science that is pushing technology, it's really the market that is pulling and needs things to happen. So this is a market analysis from Yole Development. I think everyone to you knows micro LED displays, market, industry, and technology trends 2020. This one. So the issue is, of course, that when you go to more and more advanced displays, you go down in pixel sizes. And when you are to the smartphones and the augmented reality, you're really down on the scale less than 2 micrometers. So that's, of course, a challenge, both from the fabrication, the fabs, what they can do, but also from the material side to maintain high external quantum efficiency. That is very challenging. So here you see, this is a very, very busy slide. Don't be worried. I'm not going to talk about all of these things, but it covers both assembly, backplane technologies, and the color. Let me concentrate on the color. There you see there are really two approaches. One is native RGB, where most of the industry is doing what I told you about, the blue and the green with gallium nitride and the red with gallium arsenide, aluminum gallium indium phosphide technology, while Glow has been the only one, I think I can say, until recently, doing everything with gallium nitride. Then, of course, also the color conversion with the phosphorus that many industries have been using. And, of course, as I mentioned, the nanosys and many others using quantum dots being pumped by the regular blue LEDs or OLEDs. And then I'm using quantum dots to produce the green and the red. It's the external quantum efficiency suffers when you go down to small sizes. For gallium arsenide, already at below 100 micrometers in sizes, you have issues because when you process these smaller size devices, you are limited by the fact that you have carrier diffusion, exciton diffusion, and carrier diffusion, and then reaching the defect that you form by the processing. And surface states in gallium arsenide related material, I think many of you know, is a very serious concern. It's not quite as serious for gallium nitride. Then I think you can go down to 20 microns without seeing very much of losses of the efficiencies. The picture to the right, which I will magnify now, I think you can see, this is now for the blue colors, the green colors, and the red. For standard LEDs, this, I call it orange. I guess it's sort of orange red. The yellow is for 15 micron sizes. The green is for 5 microns. This is now from the Joel development analysis. And you see that the blue, which is very efficient, as we know, 75% or so for large sizes, drops a bit, but it's still doing perfectly okay when you go down, probably also when you go down to 2 microns, but it might be down in the 15 or so % efficiency. That's my estimation. The green is still doing quite okay. This is now for the 5 micron. It's probably it's single digits when you go down to 2 microns. And the red, of course, is the real concern. For gallium arsenide, it drops very quickly for reasons that I just described about the diffusion and the non-radiative recombination. So things go down to low values already here. The same actually, if you do the gallium nitride, you're also on the scale of 5%. So if you go down to 5 micron sizes, and in both the gallium arsenide and the gallium nitride, you are down to maybe 1% or so in efficiency if you go down to 2 microns. So what should you do about that? Well, a little bit, let me describe that quickly again. So this is the type of device structures that we used when we announced the Nobel Prize for 2014. It's a vertical device structure with the PN junction and the active multiple corner wells as the emitters. And that is doing very well. If you do blue, it has I can do that already. It has an efficiency of as we know, close to 80%. For the green, you have more lattice mismatch, having to do what you need more indium in the active quantum wells. Still doing quite okay in spite of 2.7% of lattice mismatch, but it's lost compared to the blue one. While for the red, it's really very, very difficult. So you have you're almost 4% in lattice mismatch, and that's not really forgiving. You get a lot of defects in the quantum well, you get quantum confined Stark effect, and the strain induces further polarization that is disadvantageous for what you want to achieve. So what do we want? What does everyone want around the table? Maybe most of us would like to see a substrate with a lattice constant that is larger than that of the gallium nitride that would fit better with the active layer. So that's the idea. This is the idea that I had 6 years ago. I said, okay, we might not be able to grow full wafers with indium gallium nitride, but maybe we can do something that is useful for the devices. And that's what we've been working on now for over 5 years. This graph is you see vertically, you see the band gap of the gallium nitride material system with aluminum going up here, gallium aluminum nitride, and the gallium indium nitride going downwards, and versus lattice constant. So here's now the central position being gallium nitride. So if you go up here, you end up with aluminum nitride around 6 eV, and down here you're going all the way down to 0.7 eV for the indium nitride. So what I proposed was actually a very simple idea, but the Research Council liked it. I said, okay, let's see if we can copy what was done by Akasaki, Amano, and Nakamura, namely to do the blue emitting LEDs on gallium nitride. Obviously, that works very well. And then I said, okay, assume that we can make a substrate with 10% indium, then we should, with the same materials, physics, arguments, and device physics, we would have the same efficiency for the green as they demonstrated with the blue. And if we could make a 20% alloy in the substrate, we should be able to red with the same device and efficiencies. So this is what we've been working on, and now we start publishing about. The advantage with this, growing these green and the red on 10 on 20% INGAN, means that you have the same lattice. That's of course this congruent triangles here, the same type of lattice mismatch in all three cases. So what we do is to grow pyramids. I'll show you first how we grow pyramids, and we transform them into very thin slices of material. These are now indium gallium nitride platelets. They end up being that. They are fully relaxed and they are dislocation free, on top of which we can do the LEDs. So here I think you can see down here that in the small opening, just like we used to grow the nanowires, we form these perfect seeds, and they have to be very carefully controlled. That is, of course, with the skills of Soshabi primarily. And from them, we can then, instead of using conditions that grows nanowires, we can use conditions that grows a pyramid of indium gallium nitride. You see that down here, maybe a bit small, and here you see a magnification of the very tip. I think only a couple of atoms are missing in the top, which I think we have to forgive Soshabi for that, because it's actually a very nice structure. And then we use maybe some kind of a samurai sword to cut off the tip. And that's what we do. So here on gallium nitride, you have these truncated pyramids on top of which, this is the luminescence from the barrier, and this is the emission from the blue corner well. And if we do it, so this was published 2 years ago in Nano Letters, indium gallium nitride platelets for LEDs. I hope you can see that, yeah. We have a second approach for this samurai sword, and now the second approach is the following. We have these nice pyramids again. We cover it by silicon dioxide or silicon oxide, maybe less well controlled. Then we use a chemical mechanical polishing to polish down these into thin platelets. With HF, we remove the silicon dioxide, and then we have these platelets a bit rounded because of the mechanical part of the CMP process. But then you can actually use, this is what it looks like in AFM and SEM. So you have these multiple steps surrounding the top, and then if you start growing on that, the same indium gallium nitride composition, you see that this top flat surface extends radially. And then it gets more and more perfect. And when you're out here, there is not a single leaf. This is really an atomically flat, we show in this paper, atomically flat surface as seen by STM and AFM. And also then you get very, very much brighter luminescence. So this was published in the difficult year of 2020, ultra high quality INGAN platelets for relaxed platelets. Now I will almost get to the conclusion. So on top of these, we make our devices emitting blue, green, or red, depending on the composition of the templates. And these are designed and optimized as LEDs. You will see they are, as I said, less than a micron in size, but we can then also assemble them into two-dimensional arrays for larger pixels, say up to 10 microns or even larger. Here you see an example. This is now a red, this is SEM top view. Here is a single red emitting quantum well. You can see the emission. This is the barrier for 70, for 75 or so nanometers, and the quantum well emission at 625, 630. Actually, very nice emission characteristics. Here's an example of a blue quantum well with exactly the same technology, but now on gallium nitride. You can see this thin line here is the quantum well. Maybe I should have magnified it more, because if you look at the very edge here, and here for those who are device physicists, I think most of you are, you will see that the quantum well is actually shrinking. So there is a self-preservation phenomenon that the excitons or the carriers do not reach these side facets. which is a neat feature of this. We have also very nice full width of half maximum. We can do this into very, very small, I call ultra small single platelets, blue, in this case, blue nano LEDs. So a single of those is typical, in this case, 200 nanometers in size. We can push it down even further. Actually, we made this single platelet devices specifically for people doing optogenetics, wanted in this case specifically the blue photons for programmed axon outgrowth in nerve cell investigations. Also, these are very interesting light sources for ultra high resolution imaging, like biomedical imaging, which I have an ongoing project with the people in the Biomedical Imaging Center at Lund University. So we can do cathode luminescence. So this is now cathode luminescence spectrum. This is gallium nitride. This is the barrier. This is the quantum well. In this case, a green quantum well. I think I just entertain you with a little bit of CL if you are spectroscopists. So this is the gallium nitride. So you can say, why is it so black here? Well, of course, because now the platelet contains indium, so it absorbs all the gallium nitride emission. But in between, you can see gallium nitride coming from the gallium nitride below. And now you can go on and you can look at what's happening with the barrier emission. Then that shouldn't be dark, should it? No, it should be a little bit bright. And here you can see that it is. Can you see? It's a little bit bright. It looks bluish here. It should be blue. That's the color of the template. So that's the indium gallium nitride template. And here we go to the all the way to the green emitting quantum well. And it's going to climb up there. So you see the CL image to the left. So here you see now that all of these have very bright emission. It's small variations, but in principle they are very bright. When if things have gone perfectly right in the growth, which it does many times, but not always. So let me go to so you can see not always. Sometimes if things are not perfectly, it might look like this. And then we go to our friends in the TM center, Rainer Wallenberg and his team, and say, we have to look at this device in TM. Please get it up with a fib, and we will try to correlate cathode luminescence with TM, which is interesting but tedious. Now, for the sake of time, I will not talk details about this. This is looking at a red emitting quantum well, where you can actually look for all the different emission features in the devices at room temperature or low temperatures. You can also even look for specific magnesium related defect states close to the quantum well. And you can see, you can look at the red quantum well emission where that is. And yeah, lots of fun. But for the sake of time, let's stop that now. So the last 2 minutes, I will talk about what I'm doing in Shenzhen as distinguished professor and director of this new research institute. So this is the newly built engineering center. And this is the president who started exactly a year ago, actually. Xi Kongxue, who is, in my opinion, one of the brightest materials physicists, excelling in MB growth and surface science, STM, and electron spectroscopy on advanced high temperature superconductors and structural related functional devices. A very, very bright scientist. I'm extremely happy to be working together with him. So this is now the institute that has been just launched, where I will be the director. We just said visions and missions. I just say, I shouldn't expect you to read all of this, but I mean, the main emphasis is to make connections to the outside world, creating a really environmental, international environment, very much connected to Europe and to Sweden and Scandinavia. The ambition is to have a 50-50 mixtures of people with Chinese background and non-Chinese background. Very much nano-quantum sciences, electronics, photonics, and life sciences. This is actually someone who wrote my name in Chinese. It's supposed to be a joyful person and a thinker. I think that was pretty nice. So that's the mission. So this is how it's all set up. I will be the director jointly with the academician Hongqing Xu. It also feels very good. Actually, once upon a time, he got his PhD at Chalmers in Sweden, and then he was with me for 3 years as a postdoc before he was, pulled back to China to very good opportunities in the Institute of Physics. And the third person who I also enjoy very much working with, Executive Director Professor Chao Wei Sun, who is an expert in optoelectronics and quantum dots. So the research departments, the three of us that I already mentioned, myself, Hong Xing and Chao Wei, also the president with his fantastic research wants to be included in this effort. So it's going to be a big effort. So I will also like to welcome anyone from India. There are a lot of talent in India who might want to go for either PhD or postdoc or research stays in this international environment. I think it will be fantastic. I have experience from in Lund. I had a very clever person from IIT, Dr. Mukesh Kumar. Unfortunately, his stay in Lund was interrupted by this very unfortunate COVID thing that sort of stopped his engagement in Lund. So this is now my final slide. So this is a little bit of a tendentious description of this climbing up to walking from the old liquid crystal displays, the OLED displays. Don't kill me for these OLED people. And now the nano LEDs, but I think very likely it's going to become very important. So with that, I want to thank you for your attention. And I should also thank all the people that supported this research, all the agencies that supported the academic research on a very high level, and all those investors that supported the development of our company. So thank you very much for your attention.
Thank you, Samuelson. I hope you would not mind answering few questions.
Oh, I would love to. Let me see, how do I get out? I stop share. Okay, yes. Stop share.
Yeah. Hello, Professor Samuelson. Very, very nice talk and very, very inspiring also. So I also, work in the area of nitrides. So I have one technical question that these nanowires or these micro LEDs or micro wires or nanowires. So what about the surface passivation on the side wall? Because there will be a lot of surface defects. And I think these surface defects will be having more kind of like, let us say, effect when you go down from micro to nano. So how it can be like, let us say, circumvented?
Okay, that's of course a concern and an important question. First of all, these are formed continuously during the growth of the central nanowire for the LED. Then you switch growth mode in a way that you go from the actual growth only vertically to growing radially. So of course you have to, control that surface. Yes, the same way as you do when you grow any epitaxy, be that vertical or this case sideways. So it's critical how you treat the surface with 5-3 optimization and so on, and annealing experiments before you grow it radially. But I think those interfaces do not have very high defect densities. So they grow nicely and they conduct current very well. In this case, it's primarily for the electron transport out into the quantum wells. And then when you finish the whole device, of course, then you have the outermost p-doped layers, and that's where you do the contacts. That's probably less critical, I think. So I think this is not the main issue. And for the truncated pyramids, the platelets that I spoke about primarily at the end, there you have this, as I tried to explain, you have this self-passivation quantum wells actually pinching off in a way that carriers don't see the side facets.
Oh, thank you. Thanks.
Okay. Any other question?
Yeah.
So there is one talk.
Thank you very much for your
Can you read it?
How many contact people?
Rajendra,
Yeah. So, Professor Samuelson, there is a talk
I
from
forgot my glasses.
There is a question from the audience. So, yeah. So,
how chat? You tell it
in the chat. Can you see that or?
I see there is a chat down there. Yes. Let's say ask questions. Thank you for. How many contacts for 2 or 3 step lithography in EBL for 1 or 2 says I'm not able to see the bottom layer in the EBL process. Well, for these arrays of the indium phosphide nanowires, what we do is to do the polymer PMMA, for instance, but there are alternatives in which you do the E-beam or the nano imprint, most cases, and then we etch out to the semiconductor surface, and then for the 3 5s, we evaporate gold. So that gold is covering everything, the surfaces, but then we remove everything, selectively lift off. So it's only the gold that is sitting directly on the surface. So of course you optimize the thickness of that gold such that it converts into a hemisphere with the right shape. So you don't have excess gold, but that you can do very, very accurately. But that's of course an optimization. I'm not sure if that was a good answer to the question.
Yeah.
There are other questions in the chat box. If you can just look at the one below.
How do you compare existing values about 300 with LEDs in nano LEDs? Well, I say the problem is, which is really what was my motivation for this research, that when you etch down these devices into very small dimensions, you're completely dominated by the defects and the non-radiative recombination. So we see now that we have, for the macroscopic devices and our platelet devices, very similar efficiencies, of at least of the order of more than 10% efficiency. And there is no difference between the blue and the green and the red. This means that even if we go down to, say, 1.5 micron in pixel size, we will maintain the same efficiency, of the order of the same efficiency as for macroscopic devices. That is the main idea.
Okay, the last, Professor Samuelson, you can read the one below, and we can take that last.
With only contact. You saw one example, but that was a very specific case where we contacted a single platelet for this optogenetics experiment. There we used, of course, e-beam lithography and standard, nanolab procedures. For making full arrays, then you would do industrial upscaling, and we are not there yet. But I mean, there is no difference between contacting these platelets and to do it with just the processed, 2 micron or less than 2 micron size planar LED. So that's sort of standard contacting and processing. I think that's not the main challenge. I think the main challenge that a lot of people are still concerned about for the micro LED future is this assembly. How do you actually transfer and assemble the different colors onto the backplanes with high perfection? And that's not just that you should have a reasonably good yield. You actually need many nines of accuracy. I think 5 or 6 nines of accuracy in this transfer. And I think that is a big challenge. And if you don't reach that, then you have to build in, corrections, looking for errors and the maybe e-beam related corrections. I mean, there's a lot of schemes like that. So that's, of course, a big industrial scale-up challenge. People are working on it all over the world. I think from my side, I'm primarily sort of providing the new materials that can be efficient also when the pixel size is 0.5 micron. But of course, it relies on industrial development very much so. Yes. But,
okay.
So future is with micro LEDs or quantum dots for display. I would say it's probably both. I think it's micro LEDs and it is quantum dots, because that industry is moving very rapidly forward. Be that based on micro LEDs, blue micro LEDs with quantum dots, or just the micro LEDs themselves producing the 3 colors. Of course, quantum dots is not quite as good as some of us compound semiconductor guys think with our semiconductors. So I would think that probably the long-term stability would be advantageous to do everything with indium gallium nitride. That's my feeling. But of course, also the quantum dot technology is developing very much, although it gets more and more challenging. If you're going to put down these quantum dots on top of a blue emitting device that is, say, 2 microns in size, that is a huge challenge. Then it would be, in my opinion, easier to do it with the technology that I described. But we will see.
Thanks, Professor Samuelson, for an exciting talk and for answering all the questions. We saw some beautiful technology using micro LED, and I think students and faculty would be really enchanted by your talk. So thanks again, and thanks everybody for watching and joining online with us. Thank you very much.
Thank you very much.
Thank you, sir. We will start with our 6 parallel sessions as per the technical program. You all are requested to proceed to the respective halls by 11:15 a.m.
Thank you.
Thank you.
Thank you.